Okay, so I'm going to record these individually so that you can see these individually when you go to even study for your test. A particle moves along a horizontal line so that the position at any time, and this should be said or go without being mentioned, but they still write it as far as just making sure that you understand you're not going to have negative time. It's only positive time. Is given by the function of this, where x is measured in feet and t is measured in seconds. All right. So from this, immediately with this equation, what is a little bit different than what you're used to seeing? What letter up here is different than what you're used to seeing it given? The x of t. Yeah, the x of t. This x right here seems a little bit confusing. And the reason why they give x like that is because it is a horizontal line that this is moving on. Usually we give f of t. And f of t is almost like f of x. And f of x, as far as like movement and position, you have an x and a y coordinate. Because you have the point x and y, like a position. But when you have x of t, this is what it's saying. Your input is t. Your output is x of t. You with me? And what's confusing about this is that it's not going to be like a plane or a two-dimensional movement. It's going to be a one-dimensional movement. It almost looks like, if you will, it almost looks like a spring that is basically, if you're looking at it as far as just like movement, it's just like going doing, 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 and stuff like that. It's just having a horizontal movement of some kind. No up and down whatsoever. So years back on an AP test, they had a question like this, and the visual that they were showing is that they had two buildings, and suspended between the two buildings was this wire. That was a horizontal wire. And they gave something like this function that was modeling the movement, basically, of a squirrel. Now I know this is not a squirrel, but this is something close to a squirrel. Looks more like a rat. But they were saying that it had horizontal movement that would go back and forth on this line. And they gave it the function of x of t. Okay? I just want to make sure that you understand that this is a horizontal line, horizontal movement. Okay, here we go. Find the displacement, very, very important word, of the particle during the first 3 seconds. And then explain its meaning. Okay. Displacement. Some of you have heard that in physics. Okay. There's 3 words that describe displacement perfectly. What are the 3 words? Change in position. Okay? So write that down if you don't already know that, please. Change of position. So the change of position is displacement. Believe it or not, you've been doing displacement for a long time. Displacement comes from a piece of what you've been doing since Algebra 1. Guess what part of this fraction is displacement? The numerator. Change in positions is what displacement is. And what you now know it as is you now know it as f of b minus f of a over b minus a. And again, this f of b minus f of a is the change. Let me highlight that as I say it. The change between these two positions. Okay? And last but not least, with displacement, what I want you to finally put down in your notes is that it's the final position minus the initial position. So change in position, otherwise final position minus the initial position. Okay? So if I'm asking you during the first 3 seconds, what letters could I write to signify the final position? What What could I write? X of what? X of 3. And I'm going to subtract my initial position. What's my initial position? X of 0. So now what I'm going to do is I'm going to plug in 3 as my input right here into my input function, my position function. And if I plug in 3, I get 9 minus 12 plus 3. What's my initial, what's my final position? 0. Now let's plug in 0 where my t's are at. And what would I get? 3. So 0 minus 3, my displacement is negative 3 what? Negative 3 feet. Displacement is the change in position. So it will be like an f of x interpretation. It's not like feet per second. Okay? Questions? Now, real quick, find the average velocity of the particle during the first 3 seconds. So the average velocity is going to be this right here. It's the change in position, which is that, over the change in time. y2 minus y1 over x2 minus x1. And we found out that the top was a negative 3. The bottom is just 3 seconds. So what would this be? Anyone? Negative 1. What are my units? Feet per second. Okay, because this is a velocity. This is f prime interpretation. So feet per second, not feet per second squared. Okay? Now if I said to explain its meaning on both of them, kind of went too fast on that over here. This is saying that in the during the first 3 seconds, the position was displaced by a negative 3 feet. There's 3 ways that you can interpret this. If you're talking about this squirrel that I was telling you was on this AP exam, it moved back, or it moved to the left 3 feet. Another way that you could see that, negative 3, is it could be backwards. And say that you're driving on a car. You're driving in a car, negative 3 could be backwards. What's the last kind of way that you can interpret negative? Down, falling, like if you have a free falling object, so falling downward would be a negative displacement. You can, but whenever you go to say it in words, and these are the FRQ, the free response questions on the AP exam, they want you that kind of understanding. You know what I mean? And that much justification and explanation.
But like in this case, you couldn't use the falling down, right?
No, you couldn't say falling down in this case. But you could say left or backwards. So a good rule of thumb is, like the graphs for the most part, they are saying left. You know what I mean? Backwards could be like this kind of scenario where you can envision yourself walking forward or backwards like this squirrel. And then falling down could be like something being dropped from an airplane or something. Okay?
If it was going down, would it be y t?
It'd be like dy dt, right?
Like your like x of t.
Oh, nice, nice, yes. Whenever you have y of t, it doesn't necessarily mean it's a falling object, but you can interpret it like that as well. Okay? But look, here's the thing. You could even keep it as x of t as long as here you put vertical line. You know what I mean? So just make sure that you understand that variables are definitely interchangeable, but at the same time we just have to develop the understanding and meaning that they're using those variables with. Okay? So the meaning here is that during the first 3 seconds it's traveling at a rate of negative 1 feet per second on average. C. Find the particle's initial velocity and its velocity at time is 3. What do I do? Real quick, what would I do?
So I'll get the derivative of x
let's derive x of t. Because when I derive x of t, what is it that I'm using? What am I looking at?
You're looking at the velocity.
I'm looking at the velocity. So this is giving me the velocity because, again, I have to know what I'm given. The original was giving me position. Okay? And that goes back to the very, very first thing that I was saying is us understanding the different levels of these and their units and the context and interpretation that we're trying to get from them. So velocity is x prime of t. And that, anyone, what's the derivative? What's the derivative of 2t minus 4? What I'm glad that you didn't say was 2t dt dt, right? Because of that implicit chain rule, Phil. If we're in terms of t, or sorry, in terms and in respect to t, it's still going to become 1. So 2t minus 4, because we are in respect to time. All right. So find the initial velocity. What do I do with that? What does initial velocity mean? Plug in 0. X prime at 0. That's my initial velocity, because my initial time is 0. What do I get there? Negative 4. So negative 4 feet per second. And then find the velocity. Here we go. X prime of at t is 3 seconds. So anyone, what's x prime at 3? 2. 2 what? 2 feet per second. Please be careful with units, okay? And explain the meaning of each in the terms of the particle's movement. So, to me, this one's easy to interpret. It's saying that at 3 seconds, the particle is moving at a rate of 2 feet per second. You with me? And this one almost is a little counterintuitive. What's so important about this that a lot of people mistakenly overlook? Well, the negative is definitely important, but the fact that there's movement when time is what? 0. So many people do experiments and whatnot in labs to where they will throw a projectile, but it starts from 0 velocity. That's not what this is saying. This is saying, guys, when I start my timer at 0 seconds or whatever, it's already moving. So it's like if you were to see a car drive by you, and when it passes you, you start the timer. It's moving at time is equal to 0. I know it's subtle, but it's huge and overlooked. Okay. Now find the acceleration of the particle when t is 3 seconds. What do I do?
So you just get the second derivative of x of t.
Perfect. X double prime of t, anyone,
2.
is 2.
Wait, on the last one, would you say, like, at 0 seconds, it's moving left?
You could say at 0 seconds it's moving left at 4 feet per second. You could say it's moving backwards at 4 feet per second. You know what I mean? So find the acceleration of the particle when t is 3. We found the acceleration function. This is the acceleration function. Let's plug in 3. What do I get?
2.
It's still 2. Let's plug in 20. What do I get? 2. So this is a constant acceleration. Is there such a thing? Do we have constant acceleration?
Yeah.
What's our constant acceleration?
Car could accelerate.
Like a car could accelerate constantly? That'd be cool, but that'd be a souped-up car because they're always accelerating, right?
No, I mean at like at a certain point.
What do we experience on a daily basis that's constant acceleration? Gravity. Negative 9.8 meters per second squared, right? So there's constant acceleration for you as well. Okay? So this one will have a constant acceleration of 2 what?
Feet per second squared.
2 feet per second squared. Okay? Any questions from what we've done so far? And then I'm going to use the calculator here in just a bit.
We can't write like SEC because that's like secant squared, right? Per second.
Yeah, so that's what I'm saying. So you weren't here, you had come in after I said that, but SEC don't write for seconds. Just write S for seconds, because yes, the confusion is you could confuse it as secant squared. Thank you, Arjun.
So could you just say if the particle's accelerating at
per second per second?
Well, it's more asking a phrase, like.
Yeah, you could just say that the acceleration is 2 feet per second squared, or the acceleration is 2 feet per second per second. Okay? Most people use the per second squared. Alright, these last three, okay? Here we go.
What is per second per second?
So per second means this. So feet per second is a velocity. And if I do this and I take an acceleration of something, it's basically saying this over another second. So it's saying at this rate, if I were to differentiate one more level, you know what I'm saying? It's the same as dividing by seconds. Otherwise, dividing by seconds. Otherwise, keep, change, flip to where it becomes feet per second squared. See what I'm saying? Okay. When you go down the road at 50 miles an hour and you put the cruise control on, it's 50 miles an hour. But if I accelerate, you are changing, i.e. deriving, this velocity. And you're doing it over a new time. So when you derive it and you're changing it, you're going to accelerate this. So it becomes r squared. You with me? And if you were to do it one more time, you're doing something called a jerk. Okay? It's like whenever you're in a car and all of a sudden you hit a pothole, or if you're in a plane and all of a sudden you hit like a pocket of air that just drops you as far as turbulence goes, or if you're in an elevator and you're just going down the elevator and then all of a sudden someone in the elevator jumps and you feel that jerk or whatever. That's that weird feeling. That not only is it changing your velocity, it's changing the acceleration. It creates that acceleration change, which is called the jerk. Okay? I hope that visual helped. But anyway, so at t is equal to 3 seconds, is the speed of the particle, this one's big, okay? Put a big asterisk. Is the speed of the particle increasing or decreasing, and then we're going to justify. Now, yes, Omar.
Decreasing.
You say decreasing?
Oh, wait.
Roby, what do you say?
Increasing because x prime of 3 is like greater than 0.
Okay.
I say no, I say increase.
Okay, so now you're saying increasing. What's your reason? I'll get to you, Nate.
Because x prime 3 is equals to something. It's positive.
Okay. Look at this. What do you say?
X double prime is positive.
Okay. So far I have two different arguments. And physics might use different interpretations, okay? I want you to use calculus justification for your proof for this question on the AP exam, okay? Because that's the only one that they will accept. Now I need to check this out. Here we go. This is how you can determine if speed is increasing. So what I'm going to do is I'm going to pretend that this is me, and I'm facing this way, and I'm going to pretend that this is Arjun, and he's facing this way. Okay? And Arjun is going to walk with the positive velocity, and while he has a positive velocity, so let's bring Arjun back. So here we go. Arjun's going to walk with a positive velocity, and as he's walking with a positive velocity, I'm going to come up behind him with a positive acceleration, and I'm going to push him. Okay? So if his velocity, aka x prime of t, is positive, and my acceleration that I hit him with is also positive, guess what's going to happen to Arjun? he's going to speed up, right? And possibly fall, okay? But my point is, he's speeding up. Because both of the first and second derivative are both positive. Okay? So that's for speed increasing. Now, let me show you something else. They don't have to both be positive. They could both be negative. And he will still speed up. You with me? So here we go. Arjun is in red. I'm in blue. So Arjun is now going to... Oh, I got to do something real quick. A little bit clever, but no worries. I'll get it. Let me come over here. And I'm going to face the other way. And Arjun is walking backwards. Arjun's moonwalking, okay? His velocity is negative. And I think he's all fancy and everything. So I'm going to come over here with a... Whoa, not just my arms. Oh, not my... Just come on. I'm going to come with... Oh, I left my arm. So I'm going to come with a negative acceleration. And a negative acceleration... I'm going to hit him with my head. So with negative acceleration to his negative velocity, he's going to speed up. But if I have these opposite, all right, so let me bring back my arms a bit, okay? Hopefully this flip chart will let me have my arms this time. So here we go. Arjun is coming at me. Come at me, bro. He's coming at me with a positive velocity. And I'm ooh, just my arms. Oh, come on. All right, come on. So a negative, oh no. So a negative acceleration. A negative acceleration, so we'll say x double prime of t is negative. But with a positive velocity, guess what is going to happen to his speed? It's going to decrease. It's going to slow down. So all of that, of course, to make you laugh as well, if those signs are the same, if the velocity and the acceleration signs are the same, it is speeding up. But if they're different, it will be slowing down.
I just need to go.
Oh yeah, go for it. No worries. All right, so here we go. Let's go with... yeah, that's what I'm going to get to. So, yeah, don't draw pictures with no arms. So at t is 3, we first have to find what is the velocity at 3. And we also have to find what is the acceleration at 3. Guys, what's the velocity? Because we had x prime of t was 2t minus 4. What did we say x prime of 3 is? Say again? 2. 2 feet per second. But the fact that it's positive is what we're really caring about. The acceleration is what? No, not 0. It's just 2, right? So 2 feet per second squared. It doesn't matter that these are numbers. It matters what are their signs, okay? So I have a positive and I have a positive. So 2 positives, what are we going to say? Is it increasing or decreasing? Increasing. So you'll say speed is increasing. Whoops. Because the first derivative is positive and the second derivative is positive. Otherwise, x prime of t and x double prime have the same what? Have the same signs. Okay? Nice. Nicely done. During what times is the particle moving to the right? Then left. I'm going to add one right now. When is it at rest? And at what values of t does a particle change directions? And then justify. Guys, what equation am I going to be working with? Am I going to be working with the position, the velocity, or the acceleration to justify f? Say again? X prime, yeah. I'm going to look at the velocity on this. Okay? because it will be moving to the right when my velocity, otherwise x prime of t, is what? Positive. That's how I want you to write it. I don't want you can write is POS if you want, but greater than 0 is just a little bit more mathematical, saying it's positive. If it's moving to the left, it's whenever the derivative is negative. And at rest, obviously, it's going to be when the derivative is what? Equal to 0. So here we go. I know that this is my derivative function, and if I set it equal to 0 and GCF out the 2, I can see that my zeros of this function are just at time is equal to 2. So whenever I do a nice number line, and I have time is equal to 2, I'm also always going to put time problems with 0. We don't have negative time, so I'm not even worried about that. But I want to see what are the signs of these two intervals that I'm going to test right now. Okay? So I'm going to put in 1 into the derivative function that I found, my velocity function. So if I put 1 in here, what am I going to get? A negative. I don't care what the number is, I'm going to get a negative. Okay? And if I put something like 3 for my other interval, what am I going to get? A positive. So we're going to say that it's moving to the right on 2 to infinity with parentheses. Because x prime of t is positive. Guess what we will say whenever it's moving to the left? What are we going to put? On what? What interval? 0. On 0 to what? To 2. Parentheses or brackets? Parentheses on 2, but brackets. So important. Brackets at 0. Because a lot of people think that it's starting at 0, but it's not. It's already been moving at time is equal to 0. Because x prime of t is negative. It's at rest. Notice it's not on, it's at. Time is equal to 2, and you would say seconds, because, oops, x prime of t is equal to 0. Guys, can you tell me when it changes direction? Not at 0. Oh, you said 2? Okay, I'm sorry. Yes, at time t is equal to 2, it changes direction because what? Because it changes from negative to positive. It could change from positive to negative. The fact that it changes signs, that's why we want it. You see what I'm saying? Not because at 2 it's 0. Because something can have a negative velocity, stop for a moment, and have some more negative velocity. And they did that on that problem with the scroll. It had positive, it stopped for a little, and then it had more positive. It didn't change directions. It's because x prime of t changes signs. So changes directions because x prime of t changes signs. And yes, you could say what Arjun said, from negative to positive, but you don't have to be that descriptive yet. Other stuff of what's coming, you do, but not for this one.
Where did you get 2t minus t from?
I just took the derivative of the position function.
Oh.
And I GCF'd out the 2 right here to solve for the zeros of that function. The last thing that we have, what time do we leave? 3 or 4. Okay, good, perfect timing. The last thing that we have is find the total distance the particle traveled. So the total distance traveled during the first 3 seconds. And then, that's funny. Are you exhausted as the particle? Are you as exhausted as the particle? These are hefty problems. There's a lot of justification. Guys, how can I determine what's the total distance this has traveled? What can I do? I'm going to do f of b minus f of a. I'm going to do the change in position for sure, otherwise the displacement. You with me? So the displacement that occurred from final minus the initial, so look at this. What is the displacement between the final position at 2 seconds and the final position, or sorry, the initial position at 0 seconds? What did we say x of 2 was from before? On the previous slide, x of 2 was what? Or was it x of 3? Oh, that was x of 3. So let's figure out what x of 2 is. So plug in 2 into our original function, our position function, and we get what? 4 minus 8 is a negative 4, right? Plus 3 is a negative 1. Because we're trying to see what is the position at those times. Because right now we're looking at a displacement. Okay? And since we're traveling backwards from 0 to 2 seconds, we're doing after 2 seconds my final position minus my initial position of x of 0. And x of 0 would be what? 3? So we're going to say that minus 3 will get a negative 4. Go with me? Now let's do the other one. Because we have another interval, guys, of where we're traveling in a different direction. We're not asking for displacement. We're not asking what is the total displacement. We're saying what is the total distance traveled. So that means both traveling backwards and forward, what was the total distance that I traveled? Okay? So here we go. The first 3 seconds says, like right here at 3 seconds, I want final position minus that other initial position. So I'm looking at just on that interval. Okay? So x of 3 would be what? 9 minus 12 plus 3. 0. And x of 2 was negative 1. So 0 minus a negative 1 is plus 1. And this is the mistake people make. They say negative 4 plus 1 is negative 3. And they're like, ooh, this is displacement. Right now this is displacement. And at the absolute value, they think that that is the total displacement or the total distance traveled. But that's not what it is. What we need to do is be careful where we put that absolute value. We were supposed to put it right here and add it to whatever we got right here. So it should have been the absolute value of negative 4 is 4. The absolute value of 1 is 1. And then if we add it, we've traveled a total, both forward and backwards, accounting for everything, almost like everything was positive. That's why we have the absolute value signs. We've traveled a total of 5. 5 what? 5 feet. Now look, let me show you with the calculator real quick before we leave, because we do have time, how to do these easily to check on the test, because you will have the calculator and you can check and see what you got. 2 or t squared minus 4t plus 3. Here we go. T squared minus 4t plus 3. I'm going to store it as my position function x of t. Okay? And if you need to go back later and see this video, that's okay. And I'm going to go through these questions really quick just to check. The first one asked, okay, find the displacement of the particle during the first 3 seconds. The displacement, all you have to do is final position minus initial. So you'll say x of 3 minus x of 0, and you get negative 3, which is what we got. The second one says find the average velocity of this. So we're going to say the average velocity during the first 3 seconds is basically what we have here, but we're going to do it over, so that over 3 minus 0. And we get a negative 1. Okay? Find the particle's initial velocity and its velocity at 3. It's basically just saying v prime of 0, or sorry, of x prime. So here we go. This is how we do this. Menu, 4 for calculus, 2 for a derivative at a point. Yeah, so like I was saying, we're going to put this as far as finding the velocity at 3 and at 0 seconds. Okay, so let's try this again. So menu, calculus, that's number 4, 2 for a derivative at a point. And what we're going to do is we're going to say the variable is t and our value is at 0. Okay? And yes, we want to look for the first derivative. Sometimes you'll be asked to find the acceleration, so you can put the second derivative there and then just press OK. So since we have stored our function x of t, I'm just going to type it in and it will differentiate x of t and plug in this t equals 0 all at the same time. And I get a -4, just like I got back here on part C. And if I do x of 3 or x prime of 3, instead of doing that all over again, I can just scroll up twice and just press enter to copy and change this now to 3 seconds. And you get 2 just like we got by hand. Finally, find the acceleration when the particle is at 3 seconds. This is what I was talking about from before. Menu 4, 2. T is our variable. We're saying at 3 seconds. But this time we want to see the second derivative. Because our stored function is the position function x of t. When I derive it twice, it'll give me the acceleration at 3 seconds, which in this case is 2. And yes, just like we did from before, it doesn't matter what seconds, it's still going to be 2. And I'll just do one more, okay? And you see that constant acceleration is still 2. Okay, so let's finish this off. So part E says we want to see if it's increasing at 3. And I said all you have to do is look at the signs of the first and second derivative. You can come over here and say, what is the sign? So at 3 seconds, we want to know what is the sign of the velocity. What's positive, okay? So at 3 seconds, we want to know what is the acceleration at 3. And I believe we already have that up here. Yep, right here. It also is positive. So the fact that they're both positive, remember that justification, don't use the physics justification. R because is going to be written as because x prime of t and x double prime of t both have the same signs. Okay, and we wrote that right here. Okay, and they can both be negative, they can both be positive. And last but not least, the total distance of the particle that it's traveled. Now, there is an easier way to do this rather than trying to find the absolute value of each direction. And I'm talking about when it went backwards, we're talking about this one. Alright, let's try that again. To finish this up, we're looking at when it travels backwards, or to the left, from 0 to 2 seconds, we were looking at this change in position. This final minus this initial position displacement-wise, and we took the absolute value. And then when it was moving forward with a positive velocity between 3 and 2 seconds, we were looking at this. So yes, you can put this into the calculator as you see it, okay? Here we go. We're going to say the absolute value. Remember that key is right next to that number 9. And we're going to say the absolute value of x at 2 minus x at 0. And then we're going to add the absolute value. Remember, total distance traveled, we need these absolute values because we're accounting for both backward and forward displacement all in one like positive huge total, okay? And this last one was x of 3 minus x of 2. So we'll say x of 3 minus x of 2. In other words, the final position minus the initial position of that time interval, and we get 5, just like we got over here. Now, real quick, just to check it another way, I'm going to allow, there's an equation that is dealing with integrals that we're going to use the second semester, is that if we take the integral of the absolute value in respect to t of the velocity function, and we're saying from 0 to 3, which is what we're looking for these first 3 seconds, this will do immediately all of this work that we still got to know how to do it by hand because there's a calculator and a non-calculator portion to the test. But this is a good way to check it if you do have the calculator as far as looking at the total distance traveled. Because what this does is it's creating this velocity function, but it's taking the absolute value, so it's interpreting everything as positive. Okay? So if we put this into our calculator, here we go, we're going to say the integral, which we got to press that key next to the number 9, and it's this button right here. We're going to say from 0 to 3 seconds, we're going to do the absolute value of the velocity function. Now, the velocity function is not x of t that I have stored, it's the derivative of x of t. So we can come over here and quickly initiate the derivative in respect to time of x of t that we have stored. And yes, you guessed it, at the very end, it's all in respect to t. And I would get 5 very easily. I wouldn't have to do each interval by hand. So yes, you can use that as an extra way to solve for it, but please do not let it replace this information that you're going to have to know how to do by hand.